And here we go. So, class, chapter 7 is all about rotation. Alright? Some of the things that we're going to talk about, rotational motion. The first thing that we dealt with a lot yesterday is how to describe it. What are the terms, okay? Before we can measure things, before we can do calculations, before we can talk about all that stuff, we have to sort of become familiar with rotations, which is why we had our fidget spinner. Ooh, let me get mine out. Remember, today's lesson can only be taught and listened to with some sort of spinner in your hand. That's the rule. Constantly spinning to keep you aware, okay? Alright, so we talked about all the different ways of describing it. Forward rotation, backwards rotation, we talked about angles, displacement, how we can measure it, the angular velocity, all that good stuff. Here's a question. What causes something to spin? We were talking about that yesterday. A force? Yeah. In fact, I could apply a force right here at the tip, or right here kind of a little bit closer to the center. And that is going to cause a slight difference in the type of change in the velocity, the angular velocity. When you have a push or a pull in a straight line, what do we call that? A push or a pull. Something pulling stuff down to the ground. Or a force, okay? A force which causes something to rotate is called this thing. A torque. Okay? Car engine does have torque. Alright, so we're going to be talking about that. What is torque? That's actually tomorrow's lesson. How do we measure it? How do we quantify it? Alright? And guess what? Newton, he had a law for things moving, accelerating in a line. He also has a law for things that move and accelerate in a circle, rotating. Okay? So we're going to talk about Newton's second law for rotation. So all kinds of really fun stuff. Just as a reminder, we'll see this picture again. We had velocity. If something traveling in a circle, the velocity always pointed tangent to the circle. This A, what was that representing, folks? Anybody remember?
Acceleration.
Acceleration. What type of acceleration? Centripetal acceleration. And what was causing that centripetal acceleration? Force. Yes, it was a force constantly acting on the outside, and which necessitated a constantly changing velocity, specifically the direction of the velocity. Okay? So in this chapter, we're finally going to get to what I told you before. This is not going to be traveling around in a regular circle. Oh, sorry. It's going to be going faster and faster and faster and faster, or slower and slower and slower. So some of the things that we discussed, rotational motion, that's when something is spinning about an axis. We mentioned yesterday, you have to have a point of reference. You have to have a zero. Okay, so this is our zero angle. All right, and then you have to determine a positive and a negative direction. So we mentioned that. We use theta to represent that's the symbol to represent the angular position. And we have, like I said, counterclockwise is positive, clockwise is negative. And then boom, this is the first slide there on your handout. All of the things that we had with linear motion have an analog or a secret twin in the circular motion dimension. So position, x is now theta, which we are always going to measure, pretty much almost always, in radians. Okay? Velocity was the change in position over change in time. Well, when things are rotating, we have omega, the angular velocity, change in theta over change in time. That's radians per second. Linear acceleration, delta v over delta t. Angular acceleration is delta omega over delta t. Right? If we maneuver these formulas around just a little bit, we get delta x equals v delta t. That's your good old distance equals rate times time. okay? You get that same thing here with circular motion rather. Delta theta equals omega delta t. Delta v is a delta t, delta omega is alpha delta t, and then you had your delta x is v delta t plus 1/2 a delta t squared. You have that same thing over here. Delta theta is omega delta t plus 1/2 alpha delta t squared. All right, we good? So all of those formulas, like I said, that we saw before, now have their circular motion equivalents.
Are these formulas from our chart, on our chart?
I don't know. Let's go ahead and get out our formula chart. That's a good question. If there are, let's put a star next to them. That way we can know that we've got them. Got it.
There's two of them. There's theta equals theta naught plus
constant angular acceleration.
angular velocity.
Yeah, we've got this one. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Now, you could rewrite this slightly as delta theta, subtract theta naught from both sides. Theta minus theta naught equals omega naught t plus 1/2 alpha t squared. And of course, y'all know theta minus theta naught is delta theta. So just keep that in mind. That might be a good one for you to write down yourself. That's the one that's on your the handout that I gave you. So this one's on the chart. This one's on the chart. Omega equals omega naught plus alpha t. What did that one correspond to? What's his linear motion parallel secret twin? Now, one that they don't have listed is that final one. V squared equals V naught squared plus 2a x minus x naught. Let's see, can you translate that as a table? Go ahead and see if you can. Can you turn that into the circular motion secret twin? Sure. Right now?
Yes, sir.
Okay. We got the video. Camera's rolling. You should say goodbye to your future self. If there's any message you want to pass on to your past self, that would be a good time to speak to the camera.
Do your homework.
I'm also
Now, what is your future self telling you? Can you listen? Are you shouting at the screen right now, saying, "Don't do this, don't do this"? Can you hear?
Yes. I'm really confused now. So I'm just gonna wait.
I'm just saying.
Do your homework.
Something's gonna happen today that you're gonna wish you had known.
We won our game today.
Keep it one side.
It's 7 and 1 now.
All right, who's got a formula here for me? What do you think? Omega
Yes.
equals,
Omega.
how about omega squared?
Omega squared equals omega naught squared.
Keep going.
Squared. Yeah. 2 and then the alpha.
Alpha, yeah.
Alpha. And then delta.
T squared.
X minus x naught is not gonna be t squared.
Theta.
Theta minus theta naught.
Wait, so it's pretty much like the same one we used to use before, but now with the new, like.
The news.
Okay.
Yeah, just for rotation.
Okay.
Yep. We'll do some problems on that here in a second. Excuse me. I need to give you a couple other formulas. Since we're talking about formulas. I want you to think about. Alright, so you want to add this on to your paper. Well, do the derivation on your notes and then you'll with the summary at the end. What if something's going around just one time? Omega is delta theta over delta t. That's the definition. What is one rotation in radians?
2 pi.
2 pi. And yesterday, if you're going one time all the way around, what is that time? We had a special letter for that time.
T, like capital T.
Mhm.
Wait, that one's kind of on our formula sheet. It's except we have to do the algebra for it.
Right? Now remember, what we can do is we can manipulate this around. We can multiply t, both sides by t, and divide both sides by omega, and you get t equals over omega. And we saw yesterday that the period is 1 over the frequency. That formula, I believe, is on your AP chart.
But capital T is also just changing time. It could, like, I mean,
Delta T is changing time.
okay.
Uppercase T is reserved for
Oh.
period.
I see it now, okay.
Alright, next up. Let's say this thing is spinning. Spinning that way. And we have some particle, maybe it's a bug or something, I don't know, sitting there on the end. Ladybug. And he travels up to here. So it's going to go that distance right there. And it passes through, it starts off at this angle and it ends up going at this angle. So the angle that it passes through is delta theta. Okay? The distance that it would travel excuse me, is S. And if this is R, the distance from the center to the edge, then another formula, which is not on your formula chart, is that S, that arc length, is equal to the radius times theta, where theta must be in radians. Now I could prove that to you. I think we did that in pre-cal class. Do y'all remember doing that in pre-cal? S equals R theta?
Yep.
Not in pre-cal. Sorry, just you can take my word for it. So that's going to tell you. Now the neat thing is that's sort of like that's a distance. It's a length. This is a way. This is what I call a connecting formula. It connects something which is rotating, like the circular motion, like the thetas, okay, to something that you could, if you wanted to, you could flatten this out into a line, if that makes sense, like a linear distance. Like this could be in meters. This is a way of changing something that's rotating. Does that make sense? Like in radians and stuff like that, translating that over here into distance. In fact, if this was the wheel of a car, and this wheel was spinning and the car was moving forward, okay, then this right here, so if on a car, then S represents how far the car travels. R is obviously the radius of the wheel, and theta is the angle that the wheel turns through. Now, let's still consider that particle right there, and let's figure out some information about its velocity. This particle has just gone here. It's traveled this distance in that time, so its velocity, delta x over delta t. By the way, so this formula, that's a happy formula. Good one to have on your formula chart. We'll build another formula here. The velocity of that particle, it traveled, its displacement, so to speak, is s. Over a time period t, so it's got delta t. Utilizing that formula, we just found out, s is equal to r theta, so r times theta that has changed, or the theta that it's gone through, over t. So, the velocity of that point, does this look familiar to anybody? Delta theta over delta t? It's omega. That's happy formula number 2. It's a connecting formula. It's a linking formula. It's going to link the velocity in meters per second of that point on the circle, of that particle, of that bug traveling around, to its angular velocity, how fast it's spinning around. Does that make sense? This is in radians per second. So just like this formula related theta to distance, this formula right here relates angular velocity to linear velocity. And if you can imagine, if this is a car, that would tell you how fast the car is traveling, because that's how fast it's going to be moving. And the acceleration of that particle, so it's as it's moving around, it's accelerating. That's delta v over delta t. The velocity is, we saw that was r omega. So r omega t, make sure I get this right. So r times delta omega over delta t. So anybody, does that look familiar? Delta omega over delta t?
Alpha.
Alpha. That's happy formula number 3. And don't worry, there's only 3. Yes?
So the factor that converts the angular to the linear is only the radius?
Mm-hmm. Good point. Did y'all catch that? The multiplier is the radius in each case. Almost nice. There's 3 happy formulas. It's almost like you don't even have to memorize them, because you just multiply theta by r to get the distance. Multiply omega by r to get the velocity. Multiply alpha by r to get the acceleration. So S equals r theta, V equals r omega, A equals r alpha. Now, at this point, you might be asking, say, acceleration, what the heck? What acceleration is this? Is this the centripetal acceleration? And the answer is no, okay? If something is speeding up, and while it's spinning around, like for instance, if this is going kind of like that, and then I speed it up, like that, like I just sped it up, a point on the edge of that spinner is experiencing centripetal acceleration, which we've known about for chapters, as well as tangential acceleration. All right, so this is a big idea that I definitely want to make sure that we understand. We've got something that's moving around in a circle. So this is its omega. This is its angular velocity. So it's going faster and faster and faster. Does that make sense? Now, because it's going in a circle, because it is moving in a circle, what is changing at each point?
The direction.
The direction, okay? So right here, the direction looks like that. Right here, the direction looks like that. This is the velocity. The velocity vector is there. The velocity vector is there. Velocity vector looks like that, okay? So we could say, because it's moving in a circle, the velocity direction is changing. What's that? Along with the magnitude, and we'll pick that up in a second. Yes. This is what we've already talked about. The velocity direction is changing. That's going to cause centripetal acceleration. Okay? The centripetal acceleration is a vector. Okay? Its magnitude is v squared over r, and its direction is towards the center. Yes?
So centripetal is for direction, while tangential is for magnitude?
I would say it's caused by change in magnitude. Yes.
Okay.
Yep. If it's going faster and faster, or we could say if it's slowing down, but faster and faster keeps but does match our picture, then the velocity magnitude is changing, which will also cause an acceleration, but we don't call that centripetal acceleration. We call that tangential acceleration. And its magnitude, we just saw, it's equal to r alpha. And its direction is tangent to the circle. If you can wrap your mind around this, which is not too bad. I mean, we discussed all along that velocity has two parts, right? Direction and magnitude. And if the velocity changes, then you're going to get acceleration. Then logically, the velocity, if something's traveling in a circle, can change in two different manners. It could change its direction, and it could change its magnitude. And both of those will cause, by definition, acceleration. Or it's actually the other way around. It's a force which causes acceleration, which causes the change in velocity. But that's okay. The change in direction causes centripetal acceleration. Let's go. centripetal acceleration. And tangent, the circle, tangential acceleration. Okay? When I was, like I said, when I was taking physics, I struggled with this. This was something that I felt was, I never quite got. So if you can begin to understand this, then you're light years ahead of where I was when I was your age, which is great. Just as a point of clarification, we've got normal A, C, normal A of T, and then there's also this other alpha right over here. Do y'all remember what that is? So we don't delay. What's alpha?
Angular acceleration.
Angular acceleration. That's the fact that its rotational velocity is changing. Okay? Now, it just so happens that if you have angular acceleration, if it is spinning faster and faster and faster and faster, then obviously it also will have, so if you have angular acceleration, you are going to have tangential acceleration. Okay? If something's just traveling around at the same velocity, okay. What is it? Is there any change in acceleration? Angular acceleration? Or sorry, is there any change in angular velocity? No. So its angular acceleration, its alpha, is 0. And if this is 0, then r times 0 is 0. So your tangential acceleration is 0. So technically, something that's moving in a circle or maybe just sort of spinning at a constant rate is a special case of what we're talking about. It's a special case when angular acceleration equals 0. I can tell you one more thing. I mean, obviously, the velocity is perpendicular. So the velocity is tangent, the tangential acceleration, obviously, it's tangent. And both of those are always going to be perpendicular to the radius. Or you could say, I mean, the velocity is perpendicular to the centripetal acceleration. Or you could say even the tangential velocity is perpendicular. That's your, y'all remember your geometric perpendicular sign, capital T, to centripetal acceleration. You know, you've got your perpendicular symbol right there. Okay. I've got all sorts of notes. I think we're ready for some more problems. Before we move on, does anybody have any question about any of this stuff? We're at a really good point, good pause point, because this is like, that's all the theory. Now we're just gonna start solving problems. All right, here we go. S equals our theta. Yep. Oh, is that your first problem? Yes.
Oh, that's a problem. It's so small.
That is problem. Example 7.1. Find the angular velocities of the two particles in figure 7.2b. So this is one thing that happens to be spinning, kind of like this. In 5 seconds, it goes from here up to here. All right? So it goes from theta equals 0 to theta equals 90 degrees. Or, anybody know off the top of their head what that is in radians? 5 or 2. 5 or 2 radians. Okay? Go ahead.
Nothing. Just
All right.
nothing.
They want us to find angular velocity. That's omega. So the formula is omega equals delta theta over delta t. So in this case, omega is delta theta, so theta initial, theta final. So final minus initial over 5 seconds. Go ahead and walk up here, grab a calculator while I take attendance and calculate that number. Also do the same thing over here.
Do we leave it in pi or?
Now, give me full, I'm a decimal answers on these. I'm done with those exact things, yeah.
So, even though it says like delta, theta, and a little comma,
Yes,
is it just like,
that's just showing you that that's the change. We don't really know what this is, or this, what
Yeah.
those angles are.
okay,
Yeah,
so
that's-
just kind of ignore that.
They're just trying to make a little note there, I'm not sure why they're doing it.
Okay.
Technically, it looks to me like this actually is the same distance in each of these time periods.
Yeah.
So if we were able to figure out what the distance was there, then we would be able to figure out what the,
Oh, yeah, you're dividing that
Oh, I
five.
forgot about that. See, I don't have to do that.
yeah, this is just their way of saying, no, they say particle with a small angular velocity, omega undergoes a small angular displacement.
Okay.
They're just sort of making like a little note. They should not have put delta theta right there. That's good question. That's just stupid. All right, pi over 2 divided by 5, and then as a table, start working on this one. Should take you about 30 seconds.
You put a calculator in radians?
It's pi over
Are you
two divided
using
by
sine, cosine, or tangent?
this?
No.
Pi over
Then it
two
doesn't
divided
matter.
by-
No,
No.
I think both are mine.
That's pi. Oh, yeah, I got 0.0, yeah, I got
Yeah,
that.
180 is just fine.
All right,
That's what I got. Okay, ¿qué dice la siguiente también?
All right, somebody call it out. What do y'all get?
0.31.
Units?
Radian per second.
Let me just figure it out.
Mhm.
Radians per second.
What? Radian. Oh, yeah.
Radians per second. This problem. In 5 seconds, what does this particle do?
Goes
180. So what do you think is this one going faster or slower than that one?
Faster.
It is going faster. Theta naught is still 0. Theta is 180 degrees, or pi radians. And Jay, if you have questions, I can answer those on how to do the conversion just really fast. If you have a question on that. So, once again, pi minus 0, 5. Call it out to me. Here's a 0.62
0.63.
radians per second. Excuse me. All right, any questions? Let's keep going. Yeah. We know that. All right. Harley, read this problem to us, please.
A ball rolls around a circular track with a angular velocity of 4 pi radians per second. What is the period of the motion?
All right. Angular velocity. Anybody? What letter do we normally use for that? Omega. So omega equals 4 pi radians per second. When this says what is the period of the motion, what letter do we normally use for that?
T.
Capital T. I need a formula that's going to relate omega with T. Call it out to me.
2 pi over omega. Oh, sorry.
T equals 2 pi over omega. So T equals 2 pi over 4 pi.
Let's cancel out.
1/2. So half a second. So just treat these like you would any regular physics problem. Ooh, this is great. Crankshaft in your car. What did I say yesterday? What did I say crankshaft? I
So
said
it goes
like
very
You said
quick.
drive shaft.
Yes.
Yes. Probably. Alright, crankshaft of your car engine is turning at 3,000 RPM. What is its angular speed? Okay, well, we didn't quite figure this out yesterday, but close. So, 3,000 RPM means revolutions, okay, or rotations. I don't know what you're gonna call it. They're both the same thing. Per 1 minute. Now, we could be real technical. We'd be like, that is an angular speed. That is telling us how many revolutions it is in a time period.
But it wants
right?
it in radians per second.
It wants us in radians per second. Okay, so I'll put revolutions down here and radians up here. So it's 1 revolution is 2 pi radians, and I've got minutes. Cancel out minutes. Seconds right down there. So 1 minute, 60 seconds. Go ahead and give me 1 digit after the decimal. Or in fact, just round to the nearest whole number would be fine.
314.
What is it?
314.
314?
Yes.
Radians per second. That's not too bad at all, is it? So, it's just a matter of breaking down the problem. Oh, okay. So, if you remember, so take a break from the problems to go a little bit back to the theory. We had graphs with linear motion. You might want to add this to your theory notes. In fact, there were 3 different graphs. Position versus time. Keep calling out to me, what are the other ones, class?
Velocity versus time.
And
Acceleration versus time.
And guess what? 3 graphs now for circular motion. Only it's not x versus t, it's
Theta versus
theta versus t. Keep going.
Mercy.
the
Oh my God.
Omega versus time.
The not fish.
Yeah.
I read
Alpha.
Alpha.
Alpha. I don't know the name. And I don't know the name. I'm trying.
Alright.
It's a Siamese name. Yes. All right. I got it.
So back over here, the slope on a position versus time was, anybody remember?
The V value.
velocity.
The velocity.
Yeah.
The slope on the velocity versus time was the change in velocity over change in time, which was acceleration. And on this velocity graph, the area under the graph corresponded to displacement, delta x. Well, guess what? When I was teaching you all those things about linear motion, I was also teaching you the same thing secretly about circular motion, because we saw they're completely parallel, so therefore the slope on this graph is equal to, whoops, omega. The slope, by definition, is the change in omega over change in time, which is
Fish.
angular acceleration of fish. Angular acceleration, angular acceleration, I can't do that. And the area,
Delta theta.
delta theta, which is angular displacement. Big ideas. Because we've spent so much time on this stuff, I'm not going to do a ton of examples on these. I'm just going to say, hey, remember how? Yes, now apply. All right. This says the diameter of an audio compact disc is 12 centimeters. the heck is that? When the disc is spinning at its maximum rate of 500 RPM, what is the speed at a point of a distance 3 centimeters from the center and at the outside edge of the disc, which is 6 centimeters from here. So we've got this point right here, A, which is 3 centimeters, and this point over here, B, which is 6 centimeters. .500 RPM, that's how many revolutions per minute, so 540 revolutions per 1 minute. Pretty sure we're gonna calculate that into radians per second here in a minute. But let's figure out what they're asking for. This says, what is the speed of a point? Okay? What quantity are they asking for?
Velocity.
The velocity. They're talking about, and not angular velocity, they're talking about the linear velocity. How fast is this moving? Okay? If this was a little person running, how fast would they be running around? Okay? So they want us to find the velocity, the linear velocity, so to speak. Now you remember the formula that connected rotational motion with linear velocity? That formula is V equals,
R,
yeah, R times omega. So for point A, the radius is 3 centimeters, which is 0.03 meters. For this point right here, the radius is 6 centimeters, which is 0.06 meters. We've got just enough time. Let's see, I need someone fast with the calculator. So, revolution. 1 revolution, 2 pi, 1 minute, 60 seconds. So 540 times 2 pi divided by 60.
57.
57 radians per second. So therefore the velocity at A is going to be 0.03, that's the radius, times 57. And the velocity at B is going to be 0.06 times 57. The units there, meters times radians over seconds. Someone with the calculator or scale is 0.03 times 57? 1.7 meters per second. And the other one? 2.4?
14.
2.4 meters per second.
3.4.
3.4.
Did I say 2.4?
No, I said 3.4.
Okay,
I
you're
said
coughing. Yeah, I'm sorry.
3.4 meters per second. All right. There we go. We'll look at that last problem tomorrow. We'll probably postpone the subject. Have your notes anyway.
Quick reminder that FCCLA has a meeting in Ms. Bright's room this afternoon during lunch. Again, FCCLA, you're meeting in Ms. Bright's during lunch. Thank you.
Actually, I'll take that back. I'll take that back. 7-3. Don't worry about it. We'll just do problems tomorrow. How does that sound?
Do we have a meeting?
7-3. We're pushing back till Monday.
The notes?
7-3 notes we'll do on Monday.
Okay.
Do not need to have 7-3.
It's if you're going to the Christmas party.
Is it B lunch?
Yes.
Is that what
Yeah.
she
She just said during lunch, but I didn't hear for lunch.
said? It's probably B lunch.
She changed it today. I thought it was Friday. She told me.
You said Friday in the
She told me Friday yesterday.
Okay, well,